So what I'm going to do in this video is I'm going to introduce you to some of the most basic laws of logarithms that exist. We're not going to prove them here. Proving's a different concept and it's not something that I'm interested in doing at this stage. But I want to introduce you to these laws and start to look at where did they actually come from and see if we can get that picture in our mind. Like I said, this is not a proof. It's just a bit more of a hands-on demonstration to see whether we can picture where these sorts of laws come from. Like I said, for me, I think I can picture them quite well and they sort of make sense to me. And by the end of this, I'm really hoping that you'll be able to picture where these laws sort of came from, so they're sort of, they make sense to you. So the very first law, the product law. The product law says if I've got the log base A of m and I add it with the log of base A of n, that is equal to the log of base A of m times n. So these two numbers multiplied with each other. Well, to help tease this out, let's just take an example and have a look at it. Let's say I've got the log base 2 of 8 and I add it with the log of base 2 of 4. Well, if I apply this law here, that will say that I'll have the log of base A, so the base 2, the log of base 2, and I'll need to multiply these numbers together, so that'll be 8 times 4. So let's see if this works. Let's evaluate each side here and see whether in fact this is true. So to evaluate this, I need to rewrite my 8 here with a base of 2. So I need to rewrite this log base 2. So base 2 here. And what power would I need to raise this to get 8? Well, that'll be the power of 3. So you'll need to raise 2 to the power of 3 to get 8. Now, on this side here, we'll need to do the same thing. So we're adding this with the logarithm base 2. This time I'm interested to know what power of 2 would I need to raise this to get 4? Well, that'll be 2. 2 to the power of 2 will equal 4. So what that means is this part here is equal to 3. This part here is equal to 2. And we're going to add them together. So 3 plus 2 will equal 5. So if I can prove that this side over here is equal to 5, this will support the law. It will suggest that the law seems to be working, at least for this example. So over here, I'm just going to evaluate this. So this is the logarithm of base 2, 8 times 4, that'll be 32. So if I can rewrite 32 as a base of 2, that'll help me evaluate this. So this is equal to the logarithm of base 2. Now, 2 to the power of 5 will equal 32. 2 to the power of 5 will equal 32. So when I evaluate this, this will mean that this is equal to my exponent of 5. I'll need to raise the base of 2 to the power of 5 to get 32. And what you can see here is it does, in fact, equal with each other. So this does support the law at this stage. But when you initially look at this, you might get confused. For some people, it might be immediately obvious why this works, but you might get confused to what seems to be happening. Why does this seem to work? So to tease this out, let's have a look at if I've got 2 to the power of 3 and I multiply it with 2 to the power of 2. So this is now index notation. Our index law says that when we're multiplying two indices with the same base, we keep the base the same and we add the exponents. So we keep the base of 2 the same and we add the exponents. This is 3 plus the 2, which will equal 2 to the power of 5. And it's actually this property here, this index property here, that this law derives from. When we're multiplying two indices with the same base, we're actually adding the exponents together. And that's what it's saying here. We're adding the exponents together. Now, you might want to pause for a moment and just ponder that for a bit, because If you can make this connection, it helps us understand where this logarithm property comes from. Like I said, this isn't a proof. This is just sort of a hands-on demonstration about this particular property. So let's now look at the quotient law. The quotient law says that if I've got the logarithm of base a to the m and I subtract the logarithm of base a to the n, that this will be equal to the logarithm of base a of the m over n. So like last time, let's take a hands-on example. Let's say I've got the logarithm of base 2 of 32 and I subtract the logarithm of base 2 of 4. Well, applying this law here, that'll say that I'm going to have the logarithm of base 2 and I'm going to have to do 32 divided by 4. So let's evaluate this now and see where we get. So rewriting this with a base of 2, well, that'll be the logarithm base 2 to the power of 5. This one here, well, that'll be the logarithm of base 2 to the power of 2. 2 to the power of 2 will equal 4. So that means this is here is equal to 5. This here is equal to 2, so it'll be 5 subtract 2, which will be equal to 3. On this side here, we've got the logarithm of 32 divided by 4, so that'll be 8. So this will be the logarithm of base 2 of 8. Now if I rewrite 8 with a base of 2, well, that'll be equal to the logarithm base 2 to the power of 3. So this side here is equal to just the 3. And you can see here that this example has supported this law. 3 does in fact equal 3. So let's consider for a moment, where did this actually come from? Well, this comes from our dividing indices law. Let's say I've got 2 to the power of 5 divided by 2 to the power of 2. Well, when we're dividing two indices with the same base, we keep the base the same and we subtract the exponents. So that'll be 5 subtract 2. And then 5 subtract 2 will be 3. So it will be 2 to the power of 3. And this here is, in essence, really where our quotient law for logarithms comes from. That when we are dividing two indices with the same base, we keep the base the same and subtract the exponents.